Hello, everybody. It is my pleasure to open our seminar. Today we have Gia Dvali. He will tell us about demystification of a black hole. Please, Gia, 1 hour. Or a little bit more if you really.
Actually, before you will start, I will just say this, that if there will be some inappropriate annoying behavior from inappropriate people, I will mute everyone, and then in order to ask questions, you are kindly asked to raise your hand first.
Okay, good.
Thank you.
Do you see my screen now?
Now
No.
actually, we see you.
Oh, okay.
Not screen yet.
The screen was 1 minute before.
Yeah, that's right. So let me share the screen. Yeah, the thing is that I have to do some share, unshare, and then do it again because I don't know. It never the full screen. I'm trying to get it full screen. So just.
But you can push a small arrow.
Yeah, full screen.
Very small arrow in the right.
So now you don't see it, right?
We see your screen, but not full screen.
Not full screen, yeah. So this is what I have to do. Sorry. And now again. Okay.
But not so important. For me, it's okay.
Okay, now it should
be. Great, very good. Thank you.
Okay, thank you very much. I'm sorry for this technical problem. It's a great pleasure to be here and like to thank organizers. So I will discuss some approach to black holes that I was trying to develop during the last few years and trying to demystify it from a specific point of view. Some of actually the summary can be found in this paper. But okay, there are several papers. This is like a series of papers, but this is pretty informative. Okay. So I mean, everybody here knows about black holes, and we know that they are fascinating and also mysterious in certain ways. And there were certain things, certain well-accepted properties about black holes that were considered to be mysterious, actually from the beginning almost. And these are two main things are there. The rest sort of follows from these two. And so I will focus on these two. The first one is the area law of the entropy, okay? So black holes, they have Bekenstein-Hawking entropy, and this entropy scales as area in Planck units, in units of the Planck scale. And this is considered to be one of the mysteries, why the entropy scales like area of a black hole. Another mystery that is, again, it's pretty well accepted is that information is coming out very slowly. I mean, there is complete agreement that at the initial stages of evaporation, black hole radiation is thermal with a very good accuracy, and the time scale, the minimal time scale for decoding for the start of decoding information stored into a black hole is given by so-called Page's time. So this is essentially R-cube volume in Planck units. Now, and this is another mystery. Why not earlier? Because you have this object that has this extraordinary amount of quantum information stored in it, and it decays, but it's not revealing the information, okay? Until very late. So, now, what is my approach to this problem? So, whenever we encounter a mysterious phenomenon of nature, okay? So, for example, let's say, I don't know, you see a bucket of water and you see that water evaporates, and you want to understand what is it about. So there are at least two approaches. So one is to try to create a microscopic theory of whatever phenomenon you are dealing with, sort of to give a corpuscular resolution of water. So you say, okay, maybe water is made out of molecules, and the reason why it evaporates, it has this corpuscular structure, and corpuscles interact and they deplete. So that's one approach. I mean, we've been developing this approach together with collaborator of mine, Cesar Gomez, for quite some time, but I will not touch that in this talk, although the results of this talk will have impact, of course, of that picture. Actually, will justify that picture, but you can forget about that picture throughout my talk until the conclusions maybe. So in this talk, I will take a different approach. And the second approach is that when we don't understand the phenomena of nature, what we are trying to do is to look for similar effects, similar phenomena, and try to understand certain universal properties. And this is very important because, for example, you don't know what water is, but then you discover that there are other substances that behave in similar way, in certain similar ways. And this sheds a very important light because this tells you that there is underlying physics is the same for these substances. And this is a very important step towards understanding the phenomenon. And this is the approach I will take. I'll take to black holes. So therefore, the questions that I will ask, so basically my talk is about asking questions, okay? In certain sense, these questions are obvious and should have been asked long ago. So the questions are the black holes unique? Okay, we say that the area law of Bekenstein-Hawking entropy is mysterious, but how unique are black holes? I mean, what are other objects that have a similar behavior? So what are the objects that have area law of entropy? You see my cursor moving, right? So you see this equation. So S is entropy, and so what are the other objects that have similar area law entropy and similar timescale for the information retrieval? And what is the physical meaning of the scale F? So the scale F for those objects. Is gravity essential? Okay, and so on. Now, as I said, these questions are obvious, and they are the right questions actually. And they could have been asked, they should have been asked long ago, but surprisingly, shockingly, they were not. Okay, so now the point is, we need to fix the rule of the game, okay? So, okay, at least this is my approach. So I want to fix the rule of the game. And the rule of the game, which is maximally prominent, which goes beyond gravity, beyond whatever, okay? Beyond the particularities of your theory. And this most prominent rule of the game is unitarity, okay? So then the question is, so now I want to understand, answer these questions that I was asking. So the question is very simple. So for example, if I take a soliton in a theory, let's say in a renormalizable quantum field theory, a soliton, and now I ask this question, I mean, I deform my theory in such a way to give soliton a maximal entropy, maximal possible entropy. Now, maximal possible entropy with what? With the unitarity. So what happens? Okay, how different will the soliton be from a black hole? Soliton in a non-gravitational theory. Okay, so renormalizable, very nice, renormalizable, UV complete, non-gravitational theory. For example, okay. So this is the approach. And this is what I've discovered, surprisingly. And this is the message, main message of the talk. That there exists the following universal bounds on capacity of information storage, on entropy, coming from unitarity. So the first bound has the following form, that the entropy of a system, so I have a self-sustained system. And this is the system that has microstate entropy, which means that it has some degenerate microstates. And it's a device for information storage. And so the maximal entropy that this object can have by unitarity is less than its area, or equal, is equal to the area times the scale f, which is a decay constant of the Goldstone boson. Okay. Now you can ask, which Goldstone boson? Where is this Goldstone boson coming from? Maybe, okay, if theory contains some Goldstone bosons, if theory is a theory of spontaneous broken symmetry, sure, there can be some Goldstone bosons. But in a generic theory, where is the Goldstone boson coming from? Actually, the Goldstone bosons turn out to be generic. In other words, the understanding of information storage and for maximal capacity objects, we can understand beautifully in Goldstone language, actually. So the Goldstone, one universal Goldstone, which is always there, is the Goldstone of spontaneously broken Poincare symmetry. So in this talk, of course, I'm considering, maybe I should have said that, I'm considering the vacuum, which is Minkowski, and asymptotically flat, obviously, because I want to be in a consistent S-metric theory of with asymptotic, well-defined S-metric states. Okay, and so the Poincare invariance is the symmetry of the vacuum. I mean, plus additional things, but any object which is self-sustained, which can carry entropy, necessarily spontaneously breaks Poincare symmetry. You cannot have a device that stores quantum information or has entropy and is not breaking Poincare invariance spontaneously. That's impossible. Okay. So therefore, always universally exists a Goldstone boson of broken Poincare symmetry with well-defined scale f. So there is no ambiguity in defining scale f for arbitrary object. Okay. So if you give me an object which is self-sustained in quantum field theory, we can immediately define the scale f, and we can see that entropy cannot exceed that bound. The maximal entropy it can have is this, the one that I gave. Now, in addition, there are other Goldstones or Goldstone type degrees of freedom. Where are they coming from? So Poincare is universal, of course, but the others are also universal. And why? So suppose I give you an object that has a high microstate entropy, very high, of course, but we need to be close to the limit. Now, this means, of course, by default, this means that this object, a macroscopic object, can be in many different microstates, degenerate microstates. Okay? So here they are described by some sort of colors, different combinations of colors. And the number of degenerate states, of course, by definition of entropy, is exponent in power s. Now, these degenerate states, they are connected by Gapless modes because they are degenerate, these microstates. And now the point is, so the Gapless modes are there always, otherwise we cannot talk about microstate entropy. But for saturated objects, actually interesting, it's very interesting that for saturated objects, the ones that saturated down that I gave you, and I'll come back to it, they can be described as collective Bogoliubov of Goldstone modes, always, okay? So this is the set of the Goldstone modes that is responsible for the degeneracy of the microstates and information storage. In other words, what is important is that I'm not designing the system like that. I'm just saying that this is generic. If you give me a system that can store quantum information, it must have these modes. Otherwise, it's impossible. Otherwise, it doesn't have an entropy. So this is the first bound, as I said. Now, the second bound on entropy, which turns out to be related, again coming from unitarity, is that if we have a self-sustained system with interaction strength alpha, with coupling alpha, okay? So you have a device and there is certain strength of interaction, like 4-point function, 4-point interaction, that is responsible for this self-sustained state, okay? And there is a relevant coupling which is operating at scale of this object. And again, this coupling is usually well-defined. Actually, it's always well-defined. So then my point is that the entropy cannot exceed inverse of that coupling, of the running coupling. Running, I mean energy-dependent coupling, because couplings depend on momentum transfer or renormalization scale. even in non-reducible theories, they depend on energy, and evaluated at the scale of the size of the object, at the energy scale. So for momentum transfer 1/r. So that's another bound on entropy from unitarity. Now, what is the relation between these two bounds? Now, it turns so, and so where are these bounds coming from? Now, there are several arguments. Of course, I cannot go into all of them in one talk. If there will be questions, I'll be happy to answer. But generic thing is what it turns out is the following: that once you saturate this entropy bound in a theory, this is in one-to-one correspondence with the saturation of unitarity by certain scattering processes, certain scattering amplitudes, multi-particle scattering amplitudes, like few to many, so 2 to n scattering amplitudes, for occupation number, which is given by 1/alpha. Okay. So in other words, if you have a process with some center of mass energy, and you consider this process 2 to n with typical momentum transfer being 1/r, because the final state has some typical momentum 1/r, okay, of per particle. So this type of processes, they saturate unitarity, and you cannot go above simultaneously with this multi-particle state saturating the entropy bound, or any self-sustained state saturating this entropy bound. Now the thing is, the qualitatively, the way you can understand it, actually it's beautiful, and it's Lagrange physics gives us this understanding in a beautiful way. So the point is the following: that the point. So think about the cross section. Okay, so you have cross section, and this cross section takes two particles. You have high energy process with high center of mass energy. You have two particles and takes it to n. And of course, these n particles can be in many different microstates. To each particular microstate, the cross section that goes there, you can think in terms of expansion in terms of n or alpha, 1/n or alpha. So the number of final particles being occupation number 1/alpha actually represents a point of optimal truncation for the cross section. In other words, this is the point where perturbative result and non-perturbative result, they agree. So in other words, perturbative expansion in alpha of this cross section or in 1/n is ideal. Beyond that, they depart. But this point is ideal. That's why it's a point of optimal truncation. So now, if you are looking for a total cross section in going into a multi-particle state, which has many microstates, so there is an entropy, the total cross section goes as exponent 1/alpha plus s. Now, here I'm using this amazing power of large n in displaying this expression, because the point is the following: that you can see the following thing, first of all, right? You can see that if entropy exceeds 1/alpha, the cross-section will blow up and violate unitarity. Now, this violation cannot be cured by resummation, precisely because we are at the optimal point of optimal truncation. So there is no resummation that can cure it. So it's non-perturbative. The coefficient, there is a coefficient here, which I have absorbed in the cross-section. This coefficient is unimportant at large n because it only corrects, because it only depends power law on n and alpha. It only corrects the saturation point by order 1/n, and therefore it's totally negligible. Okay. Again, this is just this amazing power of large n physics. But okay, this gives you an idea about this correlation. Okay, so now, and so from here, sorry, there must be minus here. I beg your pardon. So it must be minus 1/alpha. And correspondingly, this gives the bound on unitarity, which is 1/alpha. Now, what's the relation of 1/alpha? So when the two bounds are saturated, They are saturated actually usually simultaneously. And let me explain again why they're saturated simultaneously. So the 1 over alpha, once the system reaches this 1 over alpha bound, it also reaches the area low bound. And again, the reason is physically very transparent. Again, if you consider this process 2 to n, and you are producing an n particle state. So if you are producing an n particle state, self-sustained state, which has high entropy, this n particle state breaks spontaneously Poincare symmetry. And you can figure it out pretty straightforwardly that the decay constant of the Goldstone mode scales as square root of n q, and correspondingly it scales as 1 over square root of alpha times r. Q is the momentum transfer, r is the typical size of this. And you can see now immediately that 1 over alpha, therefore, from this expression is area in units of the Goldstone decay constant. So the two bounds actually are saturated simultaneously by unitarity. Okay. Okay, so now, these are these two bounds on entropy, on information storage capacity that come from unitarity. And then there is another bound. Now we can ask a different question. So now we can ask the question, suppose you have this object that has maximal capacity of information storage, okay, saturates capacity of information storage. So saturates these bounds. So what's the time scale to extract this information from this object, okay? And there is again another universal bound that the time scale of retrieval is given by the size of the object divided by alpha, coupling constant. Now, due to the saturation relation, actually the same time scale you can rewrite in two other ways. First, it's entropy times the size of an object, and this volume times the decay constant of the Goldstone square. Okay, so this is the minimal time scale that you need to start read out of the information stored in the object. It doesn't matter whether the object is stable or unstable. Now, there
is one question, please. Who want to ask question?
Yeah, I mean, I'm just confused. These estimations you present are based on GR?
No, this has nothing to do with GR. That's the whole point of my lecture is that these things are universal and they have nothing to do whether you're working in GR or you are working in any other unitary theory. So this is universal bound independent whether you have gravity or not. So even renormalizable quantum field theory has this exactly the same area low bound as the seemingly mysterious black hole entropy. So that's the whole point. It's independent of gravity.
Yeah, may I ask a question?
Yeah,
Does boson, you deal with bosonic fields. Is it important? What happens if our nature contains only fermions?
No, it's an excellent point. So actually, this will be partially answered later when I go to QCD, because QCD is the example where fermions effectively they bosonize, they form a condensate. So yes, so in other words, of course, to have a high occupation number states in general, typically to have high occupation number states which are lumps of the fields or solitons like that, those happen in bosonic theories or in theories with fermions where fermions bosonize because they form condensates. For example, in QCD, I'll give this example. Now, there is a very interesting question that you are asking: what happens if theory has only contains fermions? I want to consider some sort of lattice of fermions and which never bosonize. Okay, so now the bound should remain the same because, as I said, even fermion collection of fermions breaks spontaneously Poincare invariance. Correspondingly, the Goldstone mode is always well defined because it doesn't matter any macroscopic state that contains capacity of information storage breaks spontaneously Poincare invariance. So the bound should hold also there, okay? But it's interesting to study particular cases with fermions how precisely the bound holds. So it's a good question, very nice question actually.
Just to confirm my understanding. So far, what you're saying is there's no new physics here. It is the standard
This is standard quantum field theory. I mean, I'm not assuming any new physics. I will not go beyond any absolutely standard quantum field theory.
So the claim is we do not, to understand black holes, we do not have to go beyond standard quantum field theory. Is that?
Well,
Yeah.
I'm giving you, okay, so that's a question of very, very nice. So that you're asking this question. So that will, I will come back to the discussion later. That's a question of interpretation. So you see, my job is to give you facts. So here I'm asking questions, and then I'm finding facts that answer these questions. Now, then we can decide what to do with these facts. The facts are extraordinary. To me, they are striking. That the absolutely theories that have nothing to do with gravity exhibit identical behavior. But we can discuss together what to do with those facts. So that would be a matter of interpretation. So we can say that this is a coincidence or something else. So, but this is a very important question you're asking. But coming back to this time scale, I want to give you one qualitative, actually very, very strong argument why this time scale is universal. Okay. And here's an argument which is extraordinarily simple, actually. Look, suppose you have an object, so you have a device, and this of certain size R, and this device has the size R, and it has a large number of microstates because it has high entropy. Okay, so there are large number of microstates exponent to this. Now the microstates have to fit. Of course, microstates have to fit within a very small gap in order to call them microstates. They have to be nearly degenerate. So at least they should fit within the gap, which is 1 over R, the size of the system. Okay. Now, this immediately tells you what should be the minimal gap, energy gap, that these memory modes, I call them memory modes, these gold stones or information carrying modes should have in order to fit there. And you will discover immediately that the minimal gap has to be 1 over S divided by R. So the largest gap, sorry, not the minimal. The largest, they cannot have gap bigger than that. Because if they have gaps bigger than that, they will not be able to fit within the delta E, and they will not belong to the same microstates. So this is 1 over S times R, or equivalently alpha divided by R, is the maximal gap that a memory mode can have in any device that stores quantum information near the saturation point. Now, it's obvious that even if we use just standard quantum mechanics intuition, if you have a mode with such a tiny gap, and you encode some quantum information in those modes, the minimal timescale on which something can happen to those modes is given by the inverse of their gap. So that's the absolute minimum timescale you need to wait before you can decode any information. Not even decode, before you can even start decoding any information from those modes. And this immediately gives this minimal timescale, okay? So that which is given by these all equivalent ways that we can write it down. So in other words, what we are learning, in a sense, we are learning something straightforward, that more efficiently we store information in a device, the longer it takes to take it out, to retrieve it. Now, let's check this for black holes, right? So obviously black holes obey both of these bounds. Because for black holes, obviously black hole breaks Poincare invariance spontaneously. It has an enormous number of goldstone degrees of freedom, so the graviton is a goldstone. Graviton modes are goldstones, and so the decay constant is given by the Planck mass. And of course, this bound that I just displayed, unitarity bound, gives black hole just saturates both. Black hole, it's well known entropy of black hole against Hawking entropy is just given by this expression. Now, minimal information retrieval time, if we take F to be Planck mass, we'll get Page's time. So black hole immediately checks. Okay, so saturates both bounds. However, the interesting thing is, what are the other objects that saturate this bound? Okay, this bound. And actually, surprisingly, I discovered that there is a huge list of objects that saturate it, and they all behave like black holes. Okay, they in virtually all the aspects they behave like black holes. The entropy is given by the area in proper units of the Goldstone mode. Actually, they even possess information horizon in semi-classically and quantum mechanically. The information retrieval time is bounded by this time scale. And those objects saturate the scattering amplitudes, unitarity of scattering amplitudes. I call them saturons for general language. Okay. Now let me give you. So now I will proceed in the following way. So first I will give you one example. I will only mention second one, and very interesting one I'll mention. And then I will consider another example which predicts new phenomena. Okay. So as one example, I chose to discuss baryons in QCD with large number of colors, because this system is extremely well studied, well understood, thanks to the works of Toft and Witten, okay, and others, and Veneziano and others. So, so therefore, there is no mystery there. We understand the system, at least at the level that is required for my talk. So this is a theory of color with a number of quark flavors. NF is the number of quark flavors. So NF labels number of quark left-right pairs of quarks, and N labels colors. Now, gluons, they interact in this theory. There's a typical coupling constant alpha, which is given by g²/2π. And this theory, so now it's useful to define, so now this theory is nice because it allows us to work in infinite weak coupling, okay? And this was realized by Toft to use this so-called Toft limit, this trick. So you can define collective coupling, lambda, which is usually we call Toft coupling, which is coupling alpha times n, color. And similarly, we can define a Toft coupling for flavor. Okay, so now why this is useful? This is useful because we can take a limit in which alpha is 0, but n goes to infinity and number of flavors go to infinity. But simultaneously, we keep collective couplings finite. And in this theory, also the QCD scale is kept finite. Okay, so what runs in this theory, the running Toft couplings run. Okay, Toft coupling runs. Color Toft coupling, for example, it runs with energy. And at some point it becomes critical, and at that point theory confines. So that's the understanding of the theory. So this limit also for flavor also was considered by Veneziano and others. So now there is a point here. By the way, there is a point that there is a critical number of flavors that we can have, beyond which theory is not becoming asymptotically free, and therefore it violates unitarity, and it doesn't make any sense. So that number, precise number is not so important, but that number is roughly, in other words, the flavors cannot exceed too much number of colors. Okay, so number of flavors and colors of the same order is the bound, and this is very informative. Now, in this theory, we have confinement and chiral symmetry breaking. So this partially answers these questions about fermions, because in this theory, what happens is the fermions, they form a condensate. So the quarks form condensate, they break spontaneously left-right symmetry down to diagonal subgroup. And in the vacuum, they exist NF-1 massless number Goldstone bosons. Okay, these are pions. There is also an additional Goldstone boson, we call it beta prime, which gets mass from Witten-Veneziano mechanism, 1/n, or from Toft mechanism from instantaneous. Now, the pion, a Goldstone boson in this theory, has a decay constant, which scales as square root of n in units of lambda QCD. So, and the pion coupling at the scale q is given by this expression, q²/π², which is given by this expression. Okay, so this is extremely well known. We are not inventing anything. Also, what is well known is that in this theory we have baryons, and these baryons have been studied thanks to works by Witten. Now the baryons are n bound states of n quarks. Okay, but nice thing about baryons is that you can think about them as from UV theory as bound states of quarks, or you can think about them from IR theory, infrared theory, as soliton of pions, okay? A so-called skyrmia. And the two descriptions are, they match each other. At large n, they're both great, okay? So I will focus my attention on this object, on the baryon. Now notice that the baryon mass with large n baryon becomes very heavy in large n limit. So it's a macroscopic object of the size of QCD scale. The radius is given by the QCD scale, and the mass is large. It's a macroscopic, nearly classical object, okay? And it's a device that stores quantum information. Why? Because baryon transforms under the flavor group. And here comes the new point. The new point is that, so my point was, since baryon is not coming as a single baryon, it comes in an enormous number of microstates. How are they different? They differ by flavor content. In other words, the flavor content of baryons, they represent microstates of one macrostate baryon. And this number is given by the representation of the flavor group under which the baryon is transforming. So my point is that baryon has an entropy because it has an enormous number of degenerate microstates. Let's see what this entropy, when this entropy saturates the bound. Now, this entropy is easy to evaluate. And you get some expression like this, and you can see that this saturates the unitarity bound, this entropy, approximately where the Toft flavor coupling is of the order 1. Now, this is very instructive because this tells you that if we wanted to give baryon more entropy that is permitted by unitarity bound, we would make theory asymptotically non-free. Actually, we would not have baryons in that theory anymore. So it's really a theory, as a self-consistent theory, it imposes this limit automatically. Of course, there's nothing we can do. It just tells us this limit on the entropy is correct. And notice that the baryon entropy in that limit is given by, most interesting is this area law. It's given by the area of the baryon, surface area of the baryon, in units of pion decay constant. Because pion decay constant is a Goldstone boson, both of the broken flavor symmetry by the baryon, and also by broken Poincare symmetry by the baryon. Okay? So it's just like a black hole. So this baryon literally behaves like a black hole. In fact, you can even compare it to black hole, and you can compare both to the memory capacity of the human brain. For instance, a black hole of the memory capacity of the human brain would have 10 to the minus 27 centimeters, and you can exactly match that with a baryon in a QCD with number of colors 10 to the 11. So it's a full legitimate state. Now, so baryon, suppose now the baryon saturates this, we take this limit when baryon saturates this bound on entropy, unitarity bound on entropy. And now the question is, how long does it take to decode quantum information encoded in the baryon? Because baryon, as I said, it has flavor content, and you can encode quantum information in its flavor content, in the sequence of different flavors of quarks. And you can use baryon to send message to your friend, no problem. So the question is how long it will take for a friend. So Bob is sending to Alice this baryon message. How long it takes for Alice to decode information encoded in the baryon, okay? By the way, also notice the following thing, that Alice, okay, this is Alice and this is baryon. And Alice naively, because the baryon entropy goes like area, naively, Alice may think that the information is on the surface, but it's not, because the goldstones occupy the bulk of the baryon. So at least in this example, we have a situation when information is given by the area, it scales by the area, but the modes are not localized necessarily on the surface of the baryon, okay? So the scaling really of the area scaling is coming from unitarity. It's not really coming from the fact that necessarily some modes have to be localized on the surface. In certain systems, they may be. That's, of course, I'm not excluding that. I'm just saying that unitarity is the most important thing that gives the area law. not the fact that the motes really are populating the surface area. So now to decode this quantum information, what Alice has to do, Alice has to scatter pions, for example. There's several ways, but all of those ways involve scattering, and therefore this takes time, precisely the time that would be analog of sort of this T minimal, which for a black hole would give pages time for a baryon. So black hole again is not special. A baryon takes exactly the same time scale to reveal its information content. Another possibility, so this is, by the way, irrespective of how hard Alice will try to get the information content out of baryon. Whether Alice tries a scattering experiment or simply makes baryon unstable. For example, you can bring baryon and anti-baryon together, and then they will annihilate, and you can just simply wait and see, and then look for the information in the content of pions that come out. And it's again the same time scale. It's a time scale again and again. It's an extremely long time scale. Now, obviously, we are not saying that there is the baryons are. It's a unitary theory. They store information. They reveal information. It's a universal phenomenon. It has nothing to do with gravity. Now, there is another example which, unfortunately, I don't have time to talk about, but actually, it's very exciting. We are very excited about this. This is Raju Vanugopalan and myself. We recently wrote a paper claiming that so-called color glass condensate in real QCD. So now you see it's beautiful because we don't need to go to hypothetical QCD with large number of colors. In real QCD, there exists a state. Actually, there is a huge evidence that there is such state exists. A so-called color glass condensate. This is thanks to all these people, Yanku, McLaren, and Kovner, Balitsky, Lipatov, Kovchagov, and others. Okay. I mean, together with Raju, of course. Raju is one of the people that is developing this picture in QCD, and this state, there is this saturated state of gluons. So this is just QCD story. Okay, so saturated state of gluons with occupation number of gluons given by the inverse coupling, inverse QCD coupling. It's the weak coupling, so it's a momentum. Energy is higher than the QCD scale, okay? So the system is at the weak coupling, high occupation number, weak coupling. So it's like a strong field, but weak coupling. And when we looked closely at this state, there is all the evidence that this state is a saturated state in our sense, in the sense of entropy. Here, sometimes there is a terminology issue. Sometimes people in QCD, sometimes people call saturation when occupation number becomes inverse coupling. But saturation that I'm referring to is saturation of the entropy bound, which requires more. Okay, so just simply having high occupation number is not sufficient. And so what we think is that and there is an evidence that this color glass condensate is very similar to a black hole because precisely it saturates all these bounds, 1 over alpha and the area low bound. Again, why? Because color glass condensate breaks spontaneously Poincare symmetry. It breaks spontaneously internal symmetries of the embedding of the color glass into a color space. And those are the gapless modes that carry quantum information. And now this is exciting because of the obvious reason, because color glass condensate, you can produce it in laboratory. And so, yeah, so it's very interesting. Now, in the remaining time, let me go to a new phenomenon, because this universality, so why it is useful to understand phenomena of nature in universal language? Because once you understand that baryon is very similar to a black hole, or a soliton is very similar to a black hole, once they are brought to near the saturation, baryons and solitons, we can understand them in theories that are under much better control, okay? And we can see that this phenomena of saturation predicts new phenomena. And then we can transport this phenomena. First of all, this is interesting because it's universal phenomena. And secondly, it's interesting because now we can apply this to black holes. Go back and say, okay, look, black holes, they also should have this property, and let's look for them. Now, I don't have time to discuss all of those. There's a list of those phenomena. I will focus on the one that I call memory burden effect. That's universal, and that's why I want to discuss this. Now, memory burden effect is something physically very transparent. And here's the point, you will understand immediately. Why, what is this memory burden about? Look, suppose you create a device. This device could be a black hole, could be a soliton, could be barium, whatever. So you create a device which is self-sustained and which allows you to store large quantities of quantum information. So I will assume that this device is so powerful that it's near the saturation point, okay, of the entropy capacity. Now, this means that this device produces environment in which collective excitations, they have very low gaps. That's why it can store enormous, large quantities of information, because you have modes there, and I call them memory modes. There are certain modes, okay, which are nearly gapless, okay? In large N, they are exactly gapless. Now, however, the same theory outside of this object, outside of the soliton, cannot provide these gapless modes. That's the whole property of the soliton. The soliton creates a special environment to have high entropy. Correspondingly, in the bulk, in the among the asymptotic states, the number of gapless modes is either non-existent or very, very small, okay? So now you can ask this question. So suppose this object carries a very large information pattern. Now this information pattern is encoded in the excitations of goldstone modes, okay? Different excitations of goldstone modes. For example, occupation numbers in 1 and 2 and 3, so on. This information pattern here, when it's inside of this object, costs very little energy, essentially no energy at large N. Okay? It cannot be taken out, because if you take it out, you have to rewrite this information into some modes, but you don't have gapless modes outside. So the information is bound to stay inside. It's as simple as that. If object decays, so what happens now if object decays? If object decays, so object starts to evaporate, let's say, okay, decays. Now you are looking at the evaporation product, and you don't see any quantum information there. And you are surprised, but there's nothing to be surprised about, because the B modes, that are the modes that take away radiation, they don't have capacity, because they don't have that many number of gapless modes, or they simply don't have any gapless modes to carry away this message. So the message is bound to stay within the system for a very long time. Otherwise, to carry it out is extremely costly in energy. Simply, system simply cannot afford that. Now, so this memory pattern sits there, okay, and back reacts. Because obviously it back reacts, because if at the end of the day, when object disappears, memory pattern has to go somewhere. And as we just said, this is very costly in energy. So therefore, it has to wait for a very long time, because it has to encode it in an extremely long wavelength mode, or it's simply just to stay there, to back react and stabilize the system. So the memory burden effect is a back reaction from the information pattern, from the memory pattern carried by a system, and it tends to stabilize the system. Okay, so simply here you have gapless memory modes, A modes, and the modes that can carry information away, they are B modes, and they have huge gaps. And B modes are simply not capable of carrying the same amount of information as was encoded in the gapless modes. So we can say that the remember brains, they live longer. So more memory is there in the device, it lives longer. Of course, this applies to devices that are close to saturation of the entropy bound. That's when the memory burden effect is important. Okay. Now, there is a toy model, a very nice toy model, which illustrates the point. Which is actually analytically solvable and also numerically. So prototype model is a vacuum bubble with spontaneous broken SUN symmetry. So imagine that you have a theory with global SUN symmetry. Okay, so the renormalizable theory, no exotica, just you write renormalizable theory with some SUN symmetry with large N. So it has a field which transforms under this symmetry, let's say a joint field, phi. And this theory has many degenerate minima. Okay, now such theories are, you can write them, I don't know, enormous number of such models, which have this degenerate minima. So let's focus on two minima. So there is a minimum with unbroken symmetry, SUN, and in this minimum, a theory has a mass gap because there are no Goldstone modes, and theory has a mass gap. And then there's a minimum with broken symmetry, and here theory contains an enormous number of gapless modes. All right. And this is the form of the field. So now let's see the following thing. Actually, I'll put movies in a couple of seconds. So now imagine you have a bubble of the vacuum. You create a bubble of the broken symmetry vacuum. This contains n-1 gapless Goldstones, which is embedded in the asymptotic vacuum is symmetric one. So in asymptotic vacuum, there are no Goldstone bosons. So there is a bubble. Inside the bubble, we have Goldstone bosons housed, a huge number of them. Outside the bubble, there are no Goldstone bosons, there's a mass gap. So inside the bubble, so a profile of the field phi is something like this, okay? Now, inside the bubble, because we have this huge number of gapless modes, we can push it towards unitarity limit and make the bubble to store enormous amount of quantum information by exciting Goldstone modes. Now, if Goldstone modes are not excited, then there is empty memory pattern in the bubble, okay? And the bubble shrinks and disappears because two vacua are degenerate. Bubble has a tension, so it shrinks and disappears, okay, decays. But if the memory pattern is occupied, the back reaction from Goldstone modes stabilizes the bubble. So the memory burden stabilizes the bubble. Okay, so now the way you can, so we have this analysis with Oleg Kaikov and Juan Sebastián Valbuena Bermudez, two students here. And so I will show the movie in a second, but actually again, it's literally a memory burden effect, because what happens is this: you have a bubble, and here you store huge memory pattern, quantum information, but in the excitations of Goldstone modes. And this is the way black hole works. That's what I want to say, okay? So this is the way, this is a prototype for a black hole, because of course the physics and gravities are different, but the principle is the same. It's universal. So black hole creates an environment in which you have gapless modes. Here also, this bubble creates an environment where you have gapless modes. And then these modes store huge amount of information. Now, this information resists the decay because the frequencies of the Goldstones inside cannot be matched by the mass gap outside, because that costs too much energy to carry the same pattern from in out. And so the system gets stabilized. Now, by the way, I will show you a movie in a second. Let me see. Let me try to show you a movie. Okay. Okay. Do you? Do you see the screen?
Yeah, we see.
Yes, yes.
Okay. So this is the vacuum bubble. What happens to vacuum bubble when the memory pattern is empty? So it just decays. Okay. So again, initial bubble just goes and disappears. Okay. This is the same vacuum bubble, but with Goldstone with information written in gold stones. So you see what happens is that this vacuum bubble is stabilized essentially by the information pattern carried by it. Okay. So let me go back to the. Standard screen. Okay, so you see the screen, right? So this is basically the reason. So now, if you think in this way, the reason why black hole cannot emit any quantum information at the initial stages of evaporation becomes obvious. It's exactly the same effect, because black hole has high entropy because it provides Doppler modes. Never mind how black hole does it. I showed how this happens for other systems, but the black hole does exactly the same. It provides Doppler modes. And there are no Doppler modes outside for the same amount of information. So that's why there is no way for a black hole to start emitting information from the beginning. So what has to happen is that the gaps of these memory modes have to grow so that sooner or finally it becomes energetically tolerable to send the information out, okay? And this is why black hole stays there for a long time without emitting any quantum information. But the memory burden, so by the way, here's an example. For example, if you have a black hole of 10 centimeter size, and you want to put a picture of a cat, for example, with pixel size 10 to the minus 66 centimeters, okay? The energy cost of the pattern outside of a black hole, this picture, simply this picture, okay? So imagine I take this picture and I encode it into a black hole with 10 centimeter size, literally, using only the knowledge we know about black holes, nothing questionable, no exotica, just simply that, right? The same pattern outside will cost 68 orders of magnitude more than it costs inside a black hole. And that's why black hole cannot give it away right away. It's very difficult. Now, we studied this system we try to now apply this knowledge to black holes together with Lucas Eisenman, Marco Mitchell, and Sebastian Zell. We try to apply this to black holes and try to understand what happens at later stages. Now, it's very important that I have to make it very clear that this memory burden effect, we see that it's universal and it's there. I don't see way how a system can avoid it, a unitary system. Now, and what we see from prototype studies is that the memory burden becomes maximal no matter what by unitarity, it becomes maximal by this time, which, by the way, matches very nicely the limit on the timescale of information retrieval. This information was not put in these simulations. So we just got it out, which agrees with this timescale of information retrieval, the bound, the start of information retrieval. So now the question is, what happens after? We don't know, okay? So what happens for a black hole? For vacuum bubbles and this, we can, of course, for renormalizable theories, we can calculate more easily. But for black holes, we know that this burden reaches maximum, meaning that standard picture of a black hole is simply not applicable, okay? There is no question of thermality, no question of self-similarity. The question is what happens after, okay? Now, it looks like what happens after is that, so here we have to rely on prototype studies. So we did prototype studies, and prototype studies show that memory burden tends to stabilize a system, a prototype system, okay? It tends to make the lifetime much longer. So the reason, okay, so there are two obvious things. So the reason is following. First, of course, by the time you reach maximal memory burden, the radiation becomes non-thermal. Okay, there is not even a trace of thermality. The deviations are order 1. So by this time, because of memory burden on a black hole, the semi-classical treatment of Hawking type, extrapolating Hawking's results to that scale becomes impossible. However, there is another thing which is very important, because you see, the standard view that was on a black hole, typically, for example, the typical assumption that people use when they calculate lifetime of a black hole, they assume that black hole evaporation is self-similar until very late stages. In other words, when black hole emits a radiation, it becomes smaller, okay? But the small black hole is almost a carbon copy of a black hole of the similar mass. Now, memory burden effect makes this impossible. Why? Because if black hole would evaporate self-similarly, this would mean that the number of memory modes and their nature should change, because the small black hole has much smaller number of gapless memory modes, and their gaps are higher. Big black hole has a different number and different nature of these modes. So then, if black hole evaporates self-similarly, what it would have to do, it had to do a complete miracle. Like, it had to be able to constantly rewrite the memory pattern from one set of modes to the other. So it's like black hole emits radiation, pattern cannot go out because of the reasons that I explained, and now it's maintained internally. So it has to rewrite from one memory mode to the other, the ones that become now important, and so on. So the question is the time scale for this available? Now, from what we see based on simulations on prototype systems, again, here we have to rely on prototype systems. We see that prototype systems are unable to do that. So there is no unitary Hamiltonian with similar scalings that you would have for black hole types, gaps, and etc. That would be able to rewrite the information pattern so fast in such an incredible speed in order to maintain self-similarity. So the conclusion is that self-similarity is not possible for a black hole. By the way, this doesn't contradict to anything, because there is absolutely no computation, reliable semi-classical computation, that proves that black hole evaporation has to be self-similar. All that was simply extrapolating Hawking's computation, which was done for a fixed radius, because in that computation, black hole is infinitely heavy. And correspondingly, this statement doesn't contradict to anything. We just simply, we never look from that point of view. Of course, this is very interesting. Oh, by the way, these are some pages from our paper, but okay, I already said that. Now here comes the speculative part. Until this point, okay, this is what we see. Now, since we see this tendency of slowing down, it looks like the black holes, after they lose half of their mass, the memory burden has become so strong that they may actually slow down the evaporation. I don't think they can be completely stabilized, because there is no reason for that. But they can dramatically slow down. This is what we see on prototypes. And for example, the regime, now of course, here comes speculation. If we assume that the slowdown lifetime of a black hole because of this memory burden is analytic in entropy, there's no reason for that. But if we assume that it's analytic in entropy, the first minimal lifetime is already very interesting, because this would, for example, open a new window for primordial black holes as dark matter candidates, and that's very nice. For example, 10 to the 8 gram black holes were never discussed before as dark matter candidates, because they were believed to be gone by now. But because of this memory burden effect, it shows that, I mean, our understanding of what happens to black holes beyond half decay in mass, half decay in mass, is absolutely far from being obvious. Oh, sorry. So I think need to wrap up. So here are my conclusions. Okay. Okay. So basically, as I said, my talk was about trying to ask questions. Okay. I tried to ask the questions that I thought were right questions for demystifying black holes. I mean, black holes are absolutely beautiful. There's no question about that. They are not. I'm not saying that they are trivial or anything like that, but the question is whether physics that governs their most mysterious properties is specific to gravity or is universal. And facts that we have discovered show that these properties are universal. So the bounds, they come from these bounds on entropy, the area law, and inverse coupling, and the time scale of information retrieval. And these bounds are physically pretty transparent. And all the systems that saturate those bounds, they behave obviously in a very similar way as black holes, as black holes do. And this also allows us to predict new phenomena that were previously not discussed because of certain assumptions about black hole physics. Since, for example, memory burden effect, that's an extremely important effect. It goes beyond black holes. That information, and it's physically very transparent, information carried by a system stabilizes it, okay? And higher is the information, longer it takes for it to come out. And black holes do exactly that, okay? And finally, as I said, I didn't mention anything about microscopic theory, but because all these examples of systems that we can understand, like solitons, baryons, this type of objects, they are in renormalizable quantum field theory, they are under control, and there we know that they are high occupation number states of quanta at the saturation point, also colored glass condensate. So this, and they exhibit same universal phenomena as black holes do. Correspondingly, logically, it sort of cries for it that black holes also most likely are multi-graviton states, multi-particle states at the saturation point, okay? And this, of course, agrees very nicely with our starting point about the import rate of black holes. But as you can see, we arrived to that from a very different perspective. Okay, let me finish here. Sorry for going a little bit over time because of these technical complications. And yeah, of course, if there are any questions, I'll be happy to discuss.
Thank you very much for your very, very interesting question. Your very interesting talk with a lot of questions. Yes, we have several questions. Maybe I will start from Gerald. Can I unmute?
No, you can ask to unmute, but it's okay.
Yes. Gerald, please ask your question.
Okay, G is a nice talk, but of course, I did ask some very similar questions as you have raised in 1985, and my answer was, well, I can mimic the behavior of a black hole very well in a semi-classical model, where I take a Schwarzschild metric, but I put a brick wall close to the horizon, just a few Planck lengths away, and I asked, how far should the brick wall be in order to mimic exactly the Hawking radiation properties? And the answer is very simple, just a few Planck lengths. And you impose a heat bath of Hawking particles far away, and then you find that the potential well is so deep that the Hawking particles generate an atmosphere very near the horizon, but outside the brick wall, of course. And that atmosphere has the same entropy as the black hole in general has. So I don't see why that's much easier, and I don't see what's wrong with such a view. Of course, it's not the solution to our problems because the brick wall comes from nowhere, but it illustrates that our problem is something very close to the horizon of a black hole.
Yeah, I mean, yes, Gerald, I absolutely, first of all, I absolutely agree that, but by the way, you answered your question. You yourself said that the brick wall is coming from nowhere. You don't know where it is coming from, and you are putting a huge assumption of an entity that you don't know whether it belongs to gravity, whether it's put by hand, or so on. However, I have absolutely no problem with this type of thought experiments. And I mean, you were one of the first, obviously, not one of the first, actually the first that precisely made this point about importance of the area for information and stuff like this. And I have absolutely no problem to experiment with black holes within gravity and try to understand better how precisely gravity works there. There is no contradiction between my approach and that approach. I'm just saying, I'm abandoning that view in this talk. I'm asking a very simple question. I'm saying, do I have similar behavior that black hole has in fully controllable renormalizable quantum theories? That's that's a well-defined question, and it turns out it has a well-defined answer. So what I'm discovering is that unitarity puts a bound on information storage capacity of arbitrary device, which is area, nothing else but area in units of Goldstone decay constant. This is a very well-defined bound. Now, when I apply it to black holes, I see the black hole saturated. So in other words, I discovered that there is certain universal property for which I don't need quantum gravity. I don't need any assumptions about brick walls or any other entity in quantum gravity. I can simply work in normalizable theories, and I'm discovering that virtually there is no property that these saturated objects have anything any different than black holes. So you can make a long list of properties that black holes have, well understood properties, I mean, and long list of properties that these objects have, and they match one-to-one up until half decay time. That's very important because that half decay time is precisely this threshold beyond which we don't understand what happens to black holes, even if we extrapolate this knowledge. So therefore, of course, that's very important to look beyond that. And that's why also this type of new mechanisms like memory burden and this type of are very important, because this is what I'm saying. So in a sense, I mean, you answered your question yourself. So there's a different program that you are following, trying to experiment with gravity, introduce certain auxiliary concepts like brick wall, put black holes in some environments. I also love doing this type of things and following this type of ideas. There's nothing wrong with them. But what I'm saying is that maybe there are different questions that we have been missing all this time.
My own answer was we just need to understand gravitational interactions between particles at the Planck scale, which
I disagree.
The effect of a brick wall. And the Shapiro effect is just the right thing to do exactly that.
Exactly. That's precisely my problem.
Ongoing particles, they interact with each other in just such a way that have the effect of a brick wall. But I'm not solving all problems at once. There are still problems there. For instance, the standard model is no good because I can only have models where all the information is sensor.
Yeah, but that's a different program. I mean, yeah,
I'm not saying that I solved.
Yeah, what I'm trying to say is that that's a different program.
Okay.
And that program is not by no means is replacing what I'm doing, because that program, of course, we should keep thinking about trying to understand interactions of particles at the Planck scale, to try to understand how gravity unitarizes, etc., etc. And we discussed several times. I have a theory of a black hole precisely based on these ideas. I think black hole is a saturated state of gravitons, and many properties of a black hole become immediately transparent in that picture. Of course, in quantum field, in physics, we cannot compute everything. There's never a possibility. There's never a theory in which we can compute everything. We always compute where we can, and then try to make some progress from there. So we always compute within the domain in which we are under control. The computation is under control. So again, I'm saying this is the question that you are bringing is like apples and oranges. I'm not entering there in this talk, but I'm saying there is a legitimate set of questions that were never asked. These questions are absolutely important to understand. Because simply the fact, what is the role of the area law? Is the area law entropy property of gravity, or the area law entropy is property of some much more fundamental underlying principle, which has nothing to do with gravity?
I found that
what I'm discovering explicitly, I'm giving you explicit facts. What I'm discovering is that the area law entropy is exhibited by all possible objects that saturate unitarity of scattering amplitudes. So
I have to remember that pure states that mixed states have to be replaced for pure states if you want them.
Of course, yeah, I'm working with pure states only because my definitions of entropy are very, very, very textbook. So my entropy is always counting number of degenerate pure microstates, and I'm working with that. Of course, yeah, sure. There's interesting thing. Actually, my students and I were trying to understand other questions like how these systems thermalize, etc. For example, Oleg Kaikov.
You see, the brick wall model has only pure states, so it has that feature in it. So
No, sure.
I'm saying that it captures basically
Sure.
the main properties of the black hole.
I have nothing against of that picture. Again, I want to make it clear that I have nothing against of that picture. But as I said, my goal in this talk was to precisely to bypass gravity, to come to gravity from a much more general understanding. Okay, and I think this is.
You know very well that I'm trying to put gravity in exclusively as an interaction at the horizon, and that works very, very well to my taste.
Well, sure. I mean, I don't absolutely. As I said, I don't have anything against of this type of line of thinking and reasoning. I'm with you there. I mean, we have to experiment with black holes, and that's an independent line of reasoning. There are many angles of the attack. I mean, they are not inter-exclusive. Okay.
Gia, is it important for you that in your example you work in 4-dimensional case, or I can imagine the same situation and 1-dimensional case, 0-dimensional case, and maybe mimic some property starting from large N matrix, 0-dimensional matrix model? What is your opinion?
Actually, that's a very good point. When I was writing formulas, I was thinking whether I should also display formulas for arbitrary number of dimensions. Then I decided it would be more complicated. I usually try to introduce as less notations as possible in the talk. So you are absolutely right. These bounds are universal in arbitrary number of dimensions. So, for example, because the unitarity works exactly the same way in arbitrary number of dimensions, and in explicit examples that I have found in all the explicit examples, this is always area. So in other words, maximal entropy from unitarity is always area in that dimension times the appropriate power of a Goldstone decay constant of broken Poincare symmetry. That's always true. That's irrespective of dimensionality. By the way, because that also works in lower dimensions, that's another thing that shows that these properties are not intrinsically gravitational. These are much more powerful properties that gravity has to obey them. And because in lower dimensions, we know that gravity sometimes it doesn't even have, depending on how far you go, propagating degrees of freedom. So that's also important, that these bounds are universal from unitarity. But yeah, thanks very much for asking this question. This is absolutely correct, yes, in all dimensions. This is true.
Okay, maybe we can go to other questions. Yes, please, Fabio Scardilli, please.
Hello.
You already unmute.
Hi, Fabio.
Hello, Gia.
Hi.
I have a question. So you say that baryon, you can define an entropy for baryon, for baryon states. So you can define also a temperature for baryon. A proton has a temperature as a black hole.
Yeah, very good. Yeah, let me tell you this. Actually, that's precisely the point here. So now the thing is that if you have so the baryon in large MQCD, if I take an isolated baryon and if I impose conservation of baryon number, the lowest state of a baryon, of course, is stable. Is stable in large N. We have to remember that. Okay, so up to 1/n corrections, essentially this is. So it behaves sort of like an extremal black hole. Now, if you put, however, if you consider unstable saturated system, for example, you can produce unstable saturated system by putting baryon, anti-baryon on top of each other, okay, close to the point of saturation, okay? So in that case, what we see preliminary indications. So the problem, we didn't manage to solve the problem completely because it's a bit tough. But what we see in the preliminary analysis is that the spectrum of pions that comes out of there is at the beginning of decay is approximately thermal. Okay, so this thermality in a sense is built in the fact that your system is made mostly out of soft quanta. You see what happens is this, right? Baryon is made mostly out of soft pions. because it's a skyrmion, right? So it's made mostly out of soft pions. So when we put baryon and antibaryon on top of each other, you have this bunch of soft pion condensate, essentially, that tries to deplete, annihilate, rescatter, and deplete. And of course, the most of the pions that are emitted, their energies are given by the inverse size of the system. Okay, so it's dominated by energy of the inverse size of the system because that's the softness of quanta. You understand what I'm saying, right? Because if you have a bunch of soft quanta, in order to deplete, they have to rescatter. So the dominant process is rescattering of few quanta, because to rescatter a large number of quanta is very costly it's a low probability, it's very costly. So you can immediately understand why the spectrum should be approximately thermal. Because, for example, suppose I put baryon and antibaryon on top of each other and they annihilate, right? Now you can ask, what is the probability to get an extremely energetic pion out of there? Okay. Now to get an extremely energetic pion, many pions have to annihilate, right? Because you need energy. But to annihilate many pions, that's costly, that's exponentially suppressed, okay? By exactly the same reason when I showed the cross section. So therefore, you will see that when baryon decays, the probability to get probability to get extremely energetic pions is exponentially suppressed. And you can confuse that with Boltzmann suppression, because Boltzmann suppression is also that to produce particles which are much more energetic than temperature, that's an exponential suppression. So that's the way, for example, this system accommodates Boltzmann type factor in these decay products. So yes, the answer to your question is that yes, from what we see so far, I haven't seen any counterexample. Always at the beginning of the decay, the spectrum is approximately thermal. Approximately, of course, because there are 1/n effects that are important. Okay.
Oh, okay, thanks.
By the way, that's another striking thing that also matches the black hole type behavior. I said that there's a long checklist of the behaviors, and they are identical to black holes. Yeah.
Okay, let's go to the next question. Norma Sanchez. Hello, Norma. Please ask your question.
Thanks very much. Hello, Irina, here from Paris. I have two points said.
Yes, sir.
The first, I completely agree about the universality of the quantum decay rates, including black holes, and independently, whatever gravity or not. In fact, Hector de Vega and myself published it in Physical Review D 2003, so almost 20 years ago, the decay rates for that, pointing out that this is for solitons, on lamps in field theories, instanton, monopoles decays, at that time topological defect decays, and so on.
Sorry to interrupt. So just to understand, so decay rate of what? What do you mean? So it's
decay rates of solitons or lamps in field theories, or instantons, or monopoles, or topological defects, and that's in similarity with a standard model of particle physics for these states, quantum set macroscopic states, or bosonization too, and also in similarity with muons and Higgs, including black holes and including strings. So and these agree. And
I don't understand, because I'm not saying that there is a universal similarity regardless of saturation of the entropy bound.
No, I am saying about decay rates. I am saying about decay rates and applied to black holes too. And in that sense, for that part, black holes in the decay at the quantum state behave for the decays as those states, which could be, I mean, you could see the paper, and the decay is very, I mean, it's very universal in some sense, which is proportional to the square of the coupling of the heavy particle set, and proportional to the mass, and a numerical factor which depends of the type of the theory you are So
no,
that
I think there is a because it's important to have the common language and common understanding.
yes,
By no means I'm saying that actually I don't think that's true, that the decay rate of arbitrary soliton is same as the decay rate of a black hole. That's simply
well,
not true.
well,
So
you can
I'm
see
saying that there is a very specific class of solitons that saturate the bound that I wrote on entropy bound, unitarity bound on entropy.
I completely agree, and I completely agree, and can be the decay rate can be expressed in terms of the entropy and in terms of the temperature or particular temperature, say, or characteristic scale temperatures you are considering in your theory. So, I mean I mean, you consider it in this way, and of course that agree with the saturation for some extreme states of the entropy, as we know that there is, I mean, black hole saturated bound of entropy and so on. Now,
no, but I mean, I don't understand. No, this is important.
Well, I address, and I want to point out for you and for the colleagues that is another, I mean, it's another way to see the universality of quantum decays of heavy particles, including black holes and including strings. Now, this is the first point. I would like to go to the second one. I mean, otherwise we cannot proceed.
Let me answer this, because by no means I want to create an impression that I'm saying that the decay rates of arbitrary solitons are similar to black holes, or behavior of arbitrary solitons are similar to black holes. Actually,
I am not saying that arbitrary.
I'm saying exact opposite. I'm saying there is a very specific class of objects in nature, and those are the objects. These are exceptional objects, exceptionally interesting and singular objects. But these are the objects that I call saturons that saturate this specific bound on unitarity, these two bounds on unitarity that I gave. Only those are the ones that are behaving like black holes. I'm not saying, actually I disagree that an arbitrary soliton can simply behave like a black hole.
I am not saying,
very cheap.
Well, okay, I mean, let us take, I have not said arbitrary solitons, I have not said arbitrary
what is your criteria?
Topological defects. So, and these are in the same class of the decay rates for muons or for other bosons, or a bosonic set bosonization. Quantum macroscopic states are as bosonization of fermions and so on. Please, I address, I mean, just take this point. Look at the paper, it's 2003, it's in the archives too, so you can see.
But I
now, I mean, please, you expressed your point, you expressed your talk. Let me also to address the second point, which is connected, because all this is connected with our common aim to understand black holes and even more said. Now, when you go to the quantum part, or said this quantum effect of making stable by the quantum memory effect or back reaction and so on. Now, that it's very important to keep in mind for black holes. Then when you reach a Planck scale and beyond, then you need to address gravity and I mean, or quantum physics, including the Planck scale physics, and then you need to distinguish which will what will happen to the models which do not contain gravity or which do not include Planck scales, and the models which include gravity or which include Planck scale. whatever you are addressing from gravity or from quantum physics. I think it's necessary to addressing from quantum physics to reach the Planck scale and beyond. And then you will have to face the problem of quantum last stage of Hawking evaporation. And I completely agree that that is not doing Hawking, Stephen Hawking extrapolation of the thermal feature. You need to do, to take said quantum back reactions and non-perturbatively. One way is as Gerard have been doing and very interesting and pointing out, and there are other ways, And so I finish now. And so I also address to consider that, to go in this direction from your program, from your schemes. There is a physical review D also of the same year. I published with Marina Ramon Medrano, last stage of Hawking evaporation, really not extrapolating, and the quantum phase transition which take place and the decays. And of course, there is no loss of information, it's unitarity, but it's not stable. There is a problem here with stability, at least if you are considering Planck scale physics, perhaps for other models you presented here or you consider. And last but not least, because I participate.
I would prefer to keep closer to the subject because I think we are diversifying. These are extremely interesting questions and issues that you are bringing, but we can talk about them privately, etc. But I would keep it closer to the subject of today's talk because obviously it was also.
It's in the today talk because. You are nicely speaking about the last stage of Hawking evaporation. One of your last slides is the conclusion about that we need to keep in mind that the last stage of Hawking evaporation or of black hole evaporation is dramatically different, etc., etc. I said that I completely agree. I already in 2003 presented explicit computation, and I don't know why we cannot say the exchange about that. Not here, but it's in the same subject you are presented.
Look, I want to avoid confusion. I don't want to confuse the listeners because these are important questions and issues that you're bringing. But I'm not saying that. I never mentioned anything about very last stage of Hawking evaporation. I never went any close to the Planck scale or anything like that. No, my point was precisely the opposite. I tried to show that these objects, all the properties are captured while we are very far from ultraviolet cutoff of the theory. And the bulk of the properties is captured while these objects are very large. So this was my point. By no means I'm against of going towards Planck scale and discussing black holes that are quantum and they evaporate. But for those black holes, entropy cannot be defined. You cannot define entropy of a black hole which has a Planck mass, because that's a meaningless statement to say the black hole Planck mass has an entropy, because it's a quantum state that decays within Planck time. There is no point in assigning any entropy to states which have very little number of microstates.
We can define always.
So I don't want to enter into those debates because those are not subject of my talk. Okay, so well, I was not entering in that discussion, in that domain, which is very important. I fully agree with you, but that's not what to say.
Entropy is a concept. You took
entropy for one particle. There is no meaning to say that one particle, which can only be in one state, has an entropy.
You have heavy particles, a composite states, and you have
for heavy ones. Yeah, if the particles are, entropy is a large N concept. This is one of the things is very important. So entropy requires becomes better and better defined in large N, when the number of constituents is large and when the number of microstates is large. when the number of microstates is small and the splitting between them is comparable, the energy splitting is comparable to the energy of the system. Of course, we can keep calling it an entropy, but it's completely useless. I mean, it's completely useless to say that electron has entropy because it can be in two states.
Well, but black holes, anyway, we all.
I got your point. I think it's, yeah.
Black holes, we all agree that have a temperature and an entropy, and even when you are going to quantum more quantum stages, you need to address the Planck scale, and then universality with other set particles or objects, quantum microscopic objects, breaks down. Because gravity is there. You need to address gravity at some point for black holes. And if you consider in particular, as you wanted to consider black holes, I mean, that keep stable and then as candidates in the early universe for other problems and so on. I mean,
okay. Thank you, Norma, for raising these very important questions. Maybe we can organize a seminar just in which you can discuss your previous talk. Let's thank you for this, for raising this question, and also Gia for his answer. And let's go to the next question. The next question is from Jack Verbashot. Hello, Jack. Please ask your question. You are unmuted, I guess. Yes, please.
No, I'm unmuted. Thank you, and Irina. And what I wondered is, in your picture, based on Goldstone bosons, what is the role of many-body chaotic states?
Yeah. So. I think I understand your question correctly, but please correct me if I answer a wrong question. Okay. So one of the questions that we were asking, this goes back a few years before this approach. So one of the questions that we were asking, when we had this idea that black hole can be described as a high occupation number, basically described as a many-body system of gravitons. Again, this is not subject of my talk today, but so in that picture we started to ask this question: under what circumstances these type of systems can become chaotic? Okay, yeah. And actually, it turns out again, very interestingly, this chaoticity of the system has to do with criticality. So how close you are, we call it criticality, how close you are to saturation. For example, in color glass condensate, the occupation number is given by inverse coupling of the system, and so it turned out that it's related with that phenomena, and also it is related with the existence of Lyapunov exponent in the system in Gross-Pitayevsky approximation. So we actually have we solved it for a bunch of us. I mean, Cesar Gomez, Nico Winterkest, Alex Pretzel, Daniel Flatzing. We solved, there is a nice one-dimensional model, actually. For example, a toy model, bosons, attractive Gazel bosons on a circle. And it turns out that model is essentially exactly solvable for this purpose. And you can trace this how the chaoticity develops in this theory as a function of Lyapunov exponent. So the time after which the system becomes chaotic as a function of Lyapunov exponent and the number of constituents. So what we got? We got that the time was equal to Lyapunov exponent times logarithm of n, and the occupation number of quanta near the critical point. So presumably this should answer your question. So therefore the conclusion is that these systems that are saturated, they can exhibit fast chaotic behavior. Now, if you let them have a Lyapunov exponent, okay? So in other words, if you, for example, if you take the system and take it in the regime of certain instability, of Lyapunov instability, then these type of systems, they can develop very fast chaoticity within logarithmic time. if you, on the other hand, stay calmly within near the saturation point, without disturbing the system to give it a Lyapunov exponent, then chaoticity time is given by actually by this very long time. This is sort of similar to the time scale of the information extraction, for example, this time scale. Okay. So does this answer your question, or maybe?
Yeah, no, it does. And it is also, if you have a complex state, the other argument is a chaotic state. It takes a very long time to overlap to a simple state, as an escape of a pion in your picture. Is that related to that time scale?
Absolutely, yes, absolutely related. Yes, absolutely. Actually, that's another way to think about the time scales of precisely this, the decoding time. Okay, for the system that is near the saturation point. But again, I want to reiterate that. So the same system, for example, think about, I don't know, let's think about barium and anti-barium, right? If I put barium and anti-barium on top of each other, very adiabatically, very nicely, in large N, it starts to decay. And then in order to extract information, I have to wait this time scale, T, okay? Which is a very, very long macroscopic time. And in order for the system to become chaotic, I also have to wait pretty long time. However, the same barium anti-barium system, you can deform in such a way to generate a Lyapunov exponent. If you do that, then that system will become chaotic much faster within logarithmic time. So the coefficient is Lyapunov exponent. So this is what comes out.
Okay, thank you.
Thank you.
Okay, the next question is from Shravan. Shravan, please ask your question.
Hi, Gia. So
Hi.
I have a couple of questions. I will try to make it very short. So first question is, you say that area law can be understood with large N quantum field theory understanding the bound states. I mean, in loose sense. Am I correct?
That's right.
Then how do you explain collapse? At what N or what number of state, critical number of states which lead the star to collapse?
You call collapse and the collapse, you mean quantum collapse, or you mean
formation of a black hole? How black hole form initially in your understanding of quantum field theory? Yeah.
Very good. So the black hole formation process that is relevant for this particular discussion is this process of 2-2M. Okay. So now I don't have transparencies here, but so you know that there is this sort of, I mean, the idea, which is, okay, it's more than an idea. There is this knowledge that black holes are formed. A classical black hole, you can form them as soon as you put enough energy within its own Schwarzschild radius. As soon as you put energy within its Schwarzschild radius, you form a black hole, right? Correspondingly, this tells you that you should form black holes also in collision of two particles, okay, right? Because if I have two particle collision, if I give these two particles sufficiently high center of mass energy, then once this energy and center of mass energy enters its own Schwarzschild radius, I have to form a black hole, okay? By the way, this was what the people that pioneered this thinking about collisions. So Gerald Toft and Gabriele Veneziano, Amati Ciappelloni Veneziano, Gross Mendel, these people. So this is a common, almost a common knowledge that we understand that black holes, you don't really need to collapse a classical object to form a black hole. You can form a black hole in a scattering of two particles. Now, this of course creates a little bit a dilemma, no, not dilemma, but a little bit a challenge, because initial two particle state is a quantum state. Okay, so you have two extremely energetic, I don't know, gravitons, for instance. Okay, but they are quantum because there are only two particles in your system of huge energy. While the final state of a black hole is classical in a good approximation. Okay, now precisely the saturation of the entropy bound is directly linked to that process. The answer is, why do you form a black hole in a two-particle collision process, why this is strange? Because naively you could say, oh, this is very strange because in two-particle collisions, this would mean that I would form a classical object. But classicality always takes a toll. It's very hard to form classical objects in collision of high energy particles because they require a lot of coherence, and that is exponentially suppressed, okay? So what is special about black hole? Well, about black hole, what is special is the black hole saturates the unitarity bound on the entropy. So exactly what happens for black hole formation in 2,2n is the gravitational version of this same scattering process in which actually this, sorry, I don't understand this. Ah, no, sorry, it was here.
Okay.
Yeah, here. Okay. So this is the cross section. This is the way it goes. Okay, so it goes 1 over alpha gravity plus the entropy. And if you plug numbers of black holes, you will see that this precisely tells you why black holes are formed with unsuppressed cross section in collision of high energy particles. Again, this has to do with the saturation of entropy in this quantum formation, in this process of black hole formation in high energy scattering. Now the classical collapse is a fully classical process, and that is, I mean that I don't see any real challenge or puzzle or fundamental question related there. I mean, exactly the same way as you can form black holes in classical, starting from some initial classical state, you can form saturated solitons also starting from initial classical state. There, I mean, the classical evolution is I don't see any big question there.
You are giving a microscopic picture how through.
Yeah, so I'm trying to give a microscopic picture of what is happening when we produce a classical object. I mean, would-be classical object. Exactly. And the microscopic picture is precisely that. It's literally here. Actually, this computation for 2,2n graviton scattering, we did it with our collaborators, Gomez, Lust, Stiberger, and so on. And also Veneziano, Addazzi, Veneziano, Bianchi, they also did similar computation, 2,2n. So it's pretty well understood, this 2,2n graviton scattering, and it's pretty well understood that the.
So now question, is it possible to derive Chandrasekhar limit with this collision?
Oh, you mean the Chandrasekhar limit for two-particle collision of a black hole formation?
Yeah.
No, with this, there is no limit. You can form arbitrary black hole in two-particle collision as long as you have sufficiently high center of mass energy. Because if the process is pure gravitational, right, then you always form a black hole. Okay, maybe what you mean is the following: if I form, if I consider a 2,2n particle scattering process with particles which interact not only gravitationally but also have some other gauge interaction, let's say repulsive interaction. Yeah. Okay. There will be a similar limit, sort of. I would not call it Chandrasekhar limit, but it would be some sort of S-matrix Chandrasekhar limit for those particular objects. What should be the impact parameter and what should be the energy in order to form a black hole? Yeah, I mean that's pretty straightforward to estimate. I mean, what you need is that the gravitational attraction dominates for that particular impact parameter and for that particular center of mass energy. Then you will always form a black hole, even if there is a slight repulsion among the constituents. But that's a good question. Yes.
Very short question in the context of cosmology. What is T minimum in the context of inflationary cosmology, and what is phase time in the context of cosmology?
Well, I mean, here, as you can see, I mean, here I'm trying to be as conservative as possible. But by the way, we have this in our community, in gravity, whatever black hole gravity community. We have this a little bit, what conservative things are a little bit upside down, because things are, things that we take to be sort of minimal and commonly accepted, in a sense, they are based on much more huge assumptions than the things that we think as exotica. And here I'm trying to be maximally conservative. So I'm considering an S-matrix theory with asymptotically flat space-time, S-matrix theory of anything, of gravity or QCD or whatever. So in this picture, I don't have any, I don't modify space-time at any distance. Of course, in case of gravity, we do have a cutoff, which is the Planck mass. And existence of black holes in gravity actually tells us that most likely we cannot probe distances smaller than the Planck length, precisely because if you try to probe distances in the collisions smaller than the Planck length, you will put enough energy to create a black hole, and so on. But I mean, but these things are pretty standard in this discussion. So I'm not assuming anything new. I'm just relying on absolutely conservative S-matrix theory, renormalizable theories even, as you can see. And that's precisely the amazing part, that those theories that have nothing to do with gravity, they give you objects which are strikingly similar to black holes. Okay, does this answer your question?
Is there any way to test your picture?
Okay, maybe.
Yeah, of course, I said that there is a memory burden effect, which is a very prominent effect, and this effect should be exhibited by an arbitrary system of saturated memory capacity. And for example, you can produce such systems in laboratory, even with cold atoms, and see the memory burden in action. And also, as I said, this has implications for primordial black holes as dark matter candidates and so on. So yeah, absolutely. I mean, these effects are real. This back reaction from a memory pattern and memory burden, they are absolutely real. Another things that can be tested is this internal entanglement. I don't have time to talk about that. Quantum breaking, and that's again another phenomena. All these interesting phenomena, they happen around this time scale. If there is no Lyapunov exponent in the system, they happen around this time scale that I gave, this time scale.
Okay.
Okay.
Thank you.
Okay, sure. Thank you.
Okay, let's go to the next questions. Luca.
Okay.
Ivanta,
It's for the next talk here. I have actually just one quick question. So as you said, as you showed, the fundamental scale that appears in this area law basically is this decay constant of some constant. Okay. So my question is, I mean, very simple. Like, given a system, is the choice of the this decay constant always unique? Or for instance, you can do cases in which not.
Yeah, thanks very much, Luca. This is a very important point. So I tried to sort of reiterate that. So in other words, the thing is that always there is always a so what matters is the largest the Goldstone constant with largest decay, the Goldstone with the largest decay constant. Okay, so actually I don't know any example in which the largest is not given by the Poincare one. Okay, so usually what happens is that the Poincare decay, Goldstone decay constant of Poincare is the one that always dominates. So that's why it's safe to express this bound through the decay constant of the Poincare Goldstone boson, which is always uniquely defined because we always know how a given system breaks Poincare invariance. But as I said, in all the examples that I know, in all the systems that contain one typical scale, these scales agree. For example, for barium, the Goldstone decay scale of Poincare invariance is exactly the same as the pion decay constant, and so on. So usually they give the same scale, but just the limit, but the bound says the largest one, which is the Poincare decay constant. Okay.
In principle, you can have like the Goldstone of the decay constant of some internal symmetry, which is different but does not appear in the area law because it's smaller than.
It can be smaller, but it cannot exceed the Poincare decay constant. So by unitarity again. So it's very hard for systems, but that you can understand very easily because you see, what is the point? Imagine you have a monopole, right? And now the monopole breaks Poincare invariance because it breaks translation invariance, it breaks space-time translation invariance, time translation invariance, Lorentz boost. Now, the monopole now can also break internal symmetries. Okay, for example, if you embed monopole in SUN theory, it does. However, the capacity of the monopole to break internal symmetry cannot exceed its capacity to break Poincare invariance. So the Goldstone decay constants of other symmetries could be less than the Poincare. That could happen, but they cannot exceed it. Because if they do, this means that somehow the theory entered the strong coupling regime and violates unitarity. Usually it happens when theory has a strong coupling somewhere, okay? But this is a very important point, yes.
Okay. The next question is from, we had a question from Alexei Yermakov, but he is not here, maybe something with connection. Okay, Luca Smaldon, please ask your question. You are still on mute. Please.
Okay, can you hear me?
Yes, yes.
Yeah, good. Okay, very nice talk. I just a curiosity about your answer to the question of Fabio Scardigli. And you talked about that pion emissions, essentially, were like an analog of the Hawking radiation in a sense.
Right. Mm-hmm.
Yeah. But it's known that Hawking radiation can be described by mechanism of Parik-Wilczek, so like tunneling effects, essentially. I was curious to know if you thought about something similar here, that it will remind me in some way the Gamow model for alpha decay. You have some sort of barrier and you have tunneling.
Yeah, that's an interesting question. No, I don't think in those terms. And probably there is some equivalent language to describe also the emission of ions in a similar language of tunneling from inside out. Yeah, I mean that would be interesting to see in that language. I'm pretty sure there would be, because you see, all the ingredients are very similar. Okay, there you have a solution, classical solution. Here you have also skyrmion. I mean, there is a solution, and yeah, I mean, there is. Yeah, I would be surprised if there is no analog of that mechanism that would operate here. But that's an interesting question. Yes, yeah. So when I was talking about the emission, I was talking in terms of annihilation of ions. So the estimate was you have a bunch of cold pions and they rescatter and annihilate, and rescatter and deplete, and that was the estimate. But yeah, it's a good point. Yes, thank you.
Thank you too. I expect you have something here, because because you say it's thermal, the thermality in Parik-Wilczek, it depends exactly on the probability of tunneling, so which is exponential. So
yeah, I mean, in other words, right. In other words, as I said, I mean, in case of in pion computation, you are looking at the cold pions rescattering and emitting and depleting, right? So that computation, of course, gives you that is the basic QFT computation. It should give you a correct answer, and that's what it gives you. It gives you approximately thermal distribution. Now, yeah, I would think that if there is a semi-classical picture of tunneling, because this computation is fully quantum, so I don't see how it can go wrong, because you are in the theory of pions and you do computation, quantum computation with pions. Now, this approach of tunneling is semi-classical more, and so yeah, I mean, if there is a correct semi-classical description, I think there should be. Then it should reproduce the same result. But as I said, I mean, computation in pion language is more fundamental, so it cannot go wrong. If there is a computation that is not matching it, that should be a problem of approximation or something.
I see.
Okay, thanks.
Okay. I think we have no more questions. Is correct? Oh.
There is Fabio.
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 Okay.
Yeah.
Please ask your question.
Yes.
Can you define in your, so to say, going back from black holes to Saturns, can you define in the Saturns something analog to the Schwarzschild radius, to the gravitational radius for Saturn.
Yeah, in terms of, yeah, absolutely. In terms of, yeah, absolutely. They possess, that's what I said in this one of the transparencies, they possess information horizon. So in other words, if the information carriers in large N limit, they see sort of a horizon. Of course, I don't know now, it's not, obviously it's not identical to but well, in a sense, I mean, even that is not, even that is close, because I mean, you have, think in the following way: you have goldstone modes that are localized within your saturate, and these goldstone modes, they do not exist outside. So there is a energy barrier for the goldstones to leak out. Energy barrier and the combinatoric factor that you have to pay, okay, the price to pay. So therefore, if you prepare a classical wave of a goldstone inside, because here horizon, of course, only happens classically. So if I do the following thing, if I take a skyrmion or take a, let's say, vacuum bubble that I showed you, yeah, vacuum bubble is even simpler. So let's take this vacuum bubble which sits there and which is saturated, and now inside, imagine I prepare a wave of a goldstone, classical wave, and I see whether this classical wave can exit the horizon, and you understand why it is extraordinarily suppressed, because because there is a difference between carriers. The carrier that lives inside cannot propagate outside. It's a collective mode. So in that sense, there is a horizon. Okay, so and it's a fully legitimate information horizon. So it locks information in. Okay, if you want, because it locks in the carriers of information.
Yeah. Very nice.
Okay.
Thank you.
Okay.
Okay.
So if there is no more question, let's stop our seminar.
Thank you very much.
Yes, Gia, thank you very much for
thank you. Thank you very much for all
interesting seminar talk, and also to patient's answer to all these questions. So thank you very much.
Thank you. Thank you.
Thank you.
Thank you.
Bye. Thank you.
Everybody, yes, bye.
Yeah, bye-bye.